Okay, so we're recording. So directional derivatives. What are these directional derivatives? What are they talking about here? All right, let me show you here. So let's say you have z and it's a function of x and y. And you want to do the partial derivative of z with respect to x. Okay. Now this is a rate of change. Okay, it's a rate of change, okay? All right. In the direction of what? There's a word I'm looking for there. And the partial derivative of z with respect to y is a rate of change. That's right, unit. Okay, so the partial derivative of z with respect to x is the rate of change in the direction of the x-axis. Okay, or in terms of a vector, it would be in the direction of the 1, 0 vector. Okay. The partial derivative. So in other words, as this surface, z is a function of x and y, and this is a surface, right? And the surface goes up and down depending on which way you move. If you move in the x direction, the surface might go up or down. If you move in the y direction, the surface might go up or down. So the partial derivative of z with respect to x, hold on. The partial derivative of z with respect to x is the rate of change of the surface as we move along the surface in the direction of the x-axis. The partial derivative of z with respect to y, on the other hand, is the rate of change, okay, of the surface in the direction of what axis? In the direction of the y-axis. That's right, Ian. Okay. And that would be in the direction of the 0, 1 vector. So these partial derivatives give rates of change of a surface in the direction of unit vectors I and unit vectors j. But what if you didn't want to move in the direction of the I vector or the direction of the j vector? What if you wanted to move, for instance, along the surface in this direction? Suppose you wanted to move in the direction of 1 over root 2, comma, 1 over root 2. Okay, what about, could we find a rate of change in this direction? And you notice, by the way, that when I say the direction, I'm always giving a unit vector. I and j are unit vectors. And in this little example here, 1 over root 2, 1 over root 2, that's a unit vector going in between the x and y axes, positive x and y axes, at a 45-degree angle. Okay, so would you agree that the surface, if we were to move along the surface, like, we're on a sled, okay, we're on a sled, and the surface is covered with snow, and we move, we're on our sled, and we slide in the direction of the vector 1 root 2, 1 root 2. Is there going to be a rate of change? Is the surface going to have a rate of change in that direction as well? Yeah, well, you know, there would be a tangent vector, but the tangent vectors we're used to finding are tangent vectors based on these partial derivatives. Okay, the partial derivative of z with respect to x and the partial derivative of z with respect to y. So you're right, the rate of change in the direction of this vector here, 1 root 2 comma 1 root 2, would involve a tangent vector, but it goes in that 45-degree angle direction. And right now, you don't know how to find that rate of change going in that direction. So that's what section 11.6 is about when they talk about directional derivatives. So if we go here to to 11.6 here, okay, they have a nice picture. Okay. Well, first of all, they start off here. Okay, giving the definition, the definition of the partial derivatives of f with respect to x and y. And you can see you're looking at how the function changes in the x direction and in the y direction, okay, for those partial derivatives. But here below, let's say you had a unit vector in the direction of AB, and it's not on one of the axes. Okay, well, what would the like we see here definitions of partial derivatives, what would the definition of the partial derivative be in this direction u? Okay, which is clearly not in the direction of the x or y axis. In other words, in figure 3 here, here's that u vector. So we have some point on the surface, some point p sub 0 consisting of coordinates x sub 0, y sub 0, z sub 0, and there's that point on the surface, and there's the tangent vector to the surface, and the tangent vector is going in what direction, class? What direction is that tangent vector moving in? Okay, and that's right, Ian. Same, if you look below in the picture there, they have a right triangle. And the tangent vector, well, can you give me a vector that it's pointing in? The direction the tangent vector is pointing in? Well, a vector though, a vector. So I see h of a, h of b. Those are components of what, well, I want to be a little careful here. So look, do you see a vector there in figure 3 in the xy plane? Is there a vector pointing in the same direction as the tangent vector? The vector u, that's right, the vector u. So the tangent vector is pointing in the direction of the vector u, and the vector u, okay, they're drawing it a little longer than the right triangle, but the vector u has components HA and HB. Okay, so you see, if we wanted to get a definition for the directional derivative, what's called the directional derivative, in the direction of the vector AB, that's going to be your directional derivative. Okay, you see that? So now you're looking at how the surface, which is the function value, changes if the going from x sub 0 to x sub 0 plus HA, and then y sub 0 to y sub 0 plus HB. That's the that is the change in the surface along the unit vector u. Okay, do you see that? I'll go back and show the picture here in figure 3. Do you see that? So what I'm trying to say is, look, you see the picture there in figure 3. The tangent vector is parallel to the unit vector u in the xy plane. The components of the vector u are HA and HB, right? Those are the components of the vector u, HA and HB, right? So that means then that the directional derivative, okay, starting at the point x sub 0, y sub 0, okay, starting there, the directional derivative, which would be the slope of that tangent line t, we would find that by computing the directional derivative you see there. Is that definition okay? All right, good, good. Are there any questions so far? Okay, all right. So the thing is, if we were to compute directional derivatives, slopes, in the direction of the unit vector AB, if we were to do that using this definition, it would be quite difficult. It would be quite difficult. Fortunately, mathematicians have come up with another way to compute a directional derivative, an easier way. Okay, this is another way to compute a directional derivative of a function in the direction of the vector u. And the vector u is always a unit vector, by the way. So what it is, the definition here, the directional derivative is a linear combination of these two partial derivatives, one with respect to x and one with respect to y. Okay, so let me see if I can give you an intuitive feel for this, okay? All right, let me go to the whiteboard and write down that definition of the directional derivative, okay, of our surface. Okay, it's going to equal a times the partial derivative of f with respect to x plus b times the partial derivative of f with respect to y. Okay. So let's take a few cases here. So case 1, let's say that our AD vector is u1. All right, so we want the directional derivative of our function in the direction of 0, 1. Okay, and incidentally, of course, A is 0 and B is 1. So, well, okay, let me write down, a few things here. Okay, can you fill in the values where the blanks are? What's going to be in the first blank? Okay, that's right, 0 and 1. So wow, it turns out that this is just equal to so I had 0 and 1. This is just equal to the partial derivative of the function with respect to y. Does that make sense? Okay, why does it make sense? Good, Hunu. What direction is the vector 0, 1 pointing in? The y-axis. Excellent, Ellie. That's what I'm looking for. Good, good. So this absolutely makes sense. Are there any questions on this? Any questions? Okay, well, let's try another vector. Let's try the vector 1 root 2 and 1 root 2. Okay, the directional derivative of our function in the direction of 1 root 2, 1 root 2 is going to be, so it's a linear combination of these first partial derivatives. Okay. But what's going to go in the blanks? What's going to go in the first blank? Okay, good. Both 1 over root 2. So it seems that the partial derivative with respect to x and y, in a sense, have equal influence on the rate of change of the surface in the direction of this vector 1 over root 2, this vector 1 over root 2, 1 over root 2. When we're looking at the rate of change of the surface in the direction of 1 over root 2, 1 over root 2, it looks like that both partial derivatives have, in a sense, an equal influence in terms of like a weighting. They each have equal influence. Why would that be? Why would that be? What can you tell me about this vector 1 over root 2, 1 over root 2 in regards to the x and y axis? Okay, I mean, here's 1 over root 2, 1 over root 2. Okay, well, but also simply speaking, okay, the 1 over root 2, 1 over root 2, the vector is blank way between the x and y axis. Halfway. Good, good. It's halfway. Halfway between. So that's why it makes sense that the influence for this rate of change in the vector in the direction of 1 over root 2, 1 over root 2 should the influence that both partial derivatives should have equal influence. Does that kind of make sense? Does that help you give you a reasonable feel, class? Is this helpful? I'm trying to promote to you an intuitive feel for why this definition is I mean, they prove it in the book, but are you okay? Are you feeling a little better about that definition? That's right. The components acts as a scalar. The A and the B, right, act as scalar multiples. That's right. That's right, Ellie. Okay, you're welcome. You're welcome. Excellent, excellent. Now, you know, we can also have directional derivatives, by the way, for functions of 3 variables too. But let's not get there yet. Okay, let's not get there yet. Let's proceed on. Let's proceed on. Okay, now another, are there any questions before I go back to the book? Okay, let me go back to the book here then. Okay, so I want to just, I want to, you know, continue on with this. We'll look at a few examples, but so the gradient vector, what is the gradient vector? Okay, well, here is the definition of our directional derivative. And notice we can write the directional derivative as a dot product of two vectors. One of the vectors is AB, and the other vector is the vector of the first partial derivatives. This vector of the first partial derivatives is called the gradient. Okay, that's called the gradient. And we have special notation for that. Let me see here, maybe I can get it on both pages here. Yeah, so, well, hold on. I'd like them both, you both to see it. I'd like to see, well, we'll just have to do it this way. Okay, so the gradient vector is a vector of the partial derivatives with respect to x and y of your function. That's called the gradient. Okay, are there any questions on this? All right, let's proceed on then. Let's proceed on. All right, so we can re-express the directional derivative then as the dot product of the gradient vector with the vector u. Notice this expresses the directional derivative in the direction of u as a scalar projection of the gradient vector onto u. Okay. Now, these rules follow for when we have a function of three variables as well. Okay, let me show you this here. So functions of three variables. Okay, so if you have a unit vector a, b, c, this is the definition of the directional derivative. Okay, and again, we could find directional derivatives using this definition, but mathematicians know that that can be difficult. It was hard enough in Calculus 1 to use the definition of the derivative to get the derivatives. It's going to be harder here. But fortunately, the directional derivative has counterpart formulas for functions of three variables. So here the directional derivative of a function of three variables is just a linear combination of the three partial derivatives with respect to x, y, and z. Okay, and are there any questions on this? Here's the gradient vector, by the way, for a function of three variables. Please let me know if you have any questions. Here's the gradient vector again, written in shorter notation. Well, Ellie, we use the gradient vector to help us compute the directional derivative. That's one thing we use the gradient vector for. But there is meaning for the gradient vector. There is an important meaning there. But here you see the directional derivative of a function of x, y, and z is just the dot product of the gradient vector with the unit vector. Well, actually, we're going to do an example right now. We're going to look at example 6, actually. We're going to look at that. We're going to look at that. Okay, so I actually have that as one of our examples. So one moment, Hyunu, we will get there. We will get there. As a matter of fact, let's get there now. Let me share this with you. Okay, let's do this example. Okay, take a moment, copy this example down, and we'll go over it. Okay, so in this problem, what we want to do is we want to find the directional derivative of this function given by x squared y cubed minus 4y at the point 2, -1 in the direction of the vector 4, in the direction of the point 4, 4. And then we're going to ask the question, is this surface increasing or decreasing in this direction starting at 2, -1? Okay, so, just imagine like, you've seen people ski, right? Ski on slopes, on surfaces. imagine, you know, you're on the mountain, and your x and y coordinates are 2, -1, and you want to ski in the direction of the point 4, 4. So your x and y coordinates are 2, -1, and you can like look in the direction of the point 4, 4. Okay, so actually, hold on. This is actually, I just thought about this. Hold on, let's try to get this. Okay, here's 2, -1. You have an x and a y axis here, and 4, 4 is over here. And so you are looking in this direction. Okay. And if you look in that direction, okay, but you're on the mountain, but your xy coordinate is 2, -1, does the surface start increasing? Does the surface increase or decrease in the direction starting at this point? In other words, if you're going to, go in that direction of that vector, are you going to be, needing to ski upward or ski downward? So what's the first thing we need to do for the directional derivative? Remember how the directional derivative is defined. The directional derivative is equal to the gradient vector dotted with the vector u. Well, certainly, we need to find partial derivatives with respect to y, but also we need our u vector. Now the u vector, is the u vector equal to this? Is it equal to, so here's the direction vector. Is it equal to 4 minus -1? Hold on. Let me just ask this before we get to the solution. Is the direction vector equal to 4 minus -1? Sorry, I should say 4 minus 2, right? 4 minus 2, comma, 4 minus -1. Is that the u vector? Excellent, Charles. Excellent. Why not, Charles? Why not? Excellent. Excellent, Ellie. Absolutely right. Absolutely right. You have to divide by the magnitude. Okay, so this here would not be the u vector. This is a common mistake students make when they get they can get the direction vector, but they forget to divide by the magnitude. Okay, well let's proceed on to the solution here. Okay, very good. So here's the direction vector u. No, here's the directional derivative. There's the definition. And as Hyunu said, we need to find the partial derivatives of the function with respect to x and y. And then we're going to compute the gradient vector. We'll get to the vector u in a moment, but let's get the gradient vector. Are there any questions coming up here to where the gradient vector is? Okay, good, good. Well, of course, now we're at the point 2, -1, so the gradient vector at 2, -1 would be computed as -4i plus 8j. Are there any questions at all? All right, may I move to the next page? Let me know. Okay. Thank you, Hanu. Thank you, Kino. Thank you, Juliana. Thank you, Madeline. Thank you, Emma. Thank you, Ellie. Okay. Well, now, to find the vector u, my vector v will be, of course, I have to subtract the points, and I get the vector 2, 5. And, you know, I could have had like, I mean, I have vector symbols here, but, you know, it might be a little more, I mean, it's fine. It's fine. All right. So the magnitude of the vector, the magnitude of the vector v, okay, this here is the magnitude of the vector v. That's going to be the square root of 29. And I multiply that by the vector 2, 5. And you get 2 over root 29 comma 5 over root 29. And now we're ready to compute the directional derivative. When we compute the directional derivative, we end up getting 32 over the square root of 29. What that means is that's the rate of change of z. Okay, the rate of change of z, of your surface. Z is a function of x and y. It's how the surface is changing in the direction of the vector u at the point 2, -1. And since that is a positive value, well, we learned that derivatives, when they have positive values, that means, you know, the function's increasing. And what they've done here in this contour plot, I mean, you might have to, I mean, it's figure 6 in the textbook, for example, 4. But what they've done is they've drawn the point 2, -1 right here. Okay, and they've drawn the vector v. The vector v points in the direction of 2, 5. So, you know, you can imagine vector v here. This vector v looks like it's going in the direction of 2, 5. They draw the gradient vector 2. Okay, so well, they draw the gradient vector in the picture. Okay, but right now, I mean, the gradient vector, you don't know. I mean, well, don't worry about the gradient vector now, but you'll be seeing why it's helpful in a moment. But let me ask you, the surface, the function f of xy, if you recall, was equal to x squared y cubed minus 4y. Now, we didn't use MATLAB, we didn't use the easy surf command to graph this function, but what, you know, you'll notice this vector v, I mean, it's pointing in the direction of the, you know, of the first quadrant here, right? Okay, first quadrant, quadrant 1. This function, I mean, what happens to the x and y values as you move in the direction of v in quadrant 1? What happens to the x and y values? They increase. And let me ask you this. That's right. What happens to the function? I mean, yeah, you have the function here. It's x squared y cubed minus 4y. As x and y get large, what's that surface going to do as you move out in the first quadrant? It's going to increase in z. Absolutely. It's kind of obvious. And looking at the contour plot, what's happening here? What's happening to the contour lines as you move in the direction of the vector v? You're getting closer together. The level curves are getting closer together, and therefore the surface is getting steeper. Okay. Now, level curves, when they get close together, a surface could be getting steeper, or it could be getting like, it could be, you know, going up. It could be getting steeper in the upward direction, or it could be getting steeper in the downward direction. But in this case, it's in the upward direction. Okay, are there any questions on that? Okay. May we move to another example? Okay, Ellie, very good. And I want to make sure, Madeline, good. It's nice to hear from some other folks here, you know, chat, thumbs up and all that. I really like hearing from everybody. I really do, you know. All right, great. Let me see here. Let me just see. Okay. All right, great. Wonderful. Well, let's move forward here. Let's look at another example, okay? Let me give you a moment to copy this example down. Okay, so now we have a function, f of xy equals x times e to the y. And now we're asking, in what direction does the function have a maximum rate of change at the point 2, 0? So a maximum rate of change, so we could, I mean, if we, I'll just draw an xy axis here. Come on, give it to me straight. I want a straight line. And let me put the point 2, 0 here. Got to click on things properly. Okay, there's 2, 0. And so, there's a surface above the xy plane. The surface is given by this function. Okay, and there are all kinds of directions that we could look in, right? How many directions, possible directions, are there coming out of the point 2, 0? Like in terms of, directional derivatives, how many directional derivatives could we compute if we wanted? How many? Good, Charles. Good, you knew. Infinite number. An infinite number. Because the angle goes from 0 to 360. We could rotate 0 to 360. So definitely an infinite number. Okay, and actually I'll mention one thing here. Directional derivative of a function of x and y, right? You learn that's the gradient of the function. Well, hold on. I'm mentioning this because Xiunu mentioned about, brought in an angle here. He was talking about an angle. So the definition is of course the dot product of, well, no, hold on. Let me be more clear here. Okay, so this was the first definition, right? But any vector AB, okay, is going to have an angle theta that goes with it, right? So you could write A as cosine theta and B as the sine of theta. I mean, in other words, if you're given an angle theta, if you're just told that the vector points like 135 degrees, okay, well, you can find the components of the vector A and B, the unit vector that points, 135 degrees from the positive x-axis. That would be pointing in the second quadrant, by computing the cosine and the sine of the angle. And that's naturally going to give you a unit vector. Just wanted to mention that. But here, what direction does F have the maximum rate of change? Well, there's a very special direction. So we can't test out all these directions, right? We never get the answer, right? So what we have to do is we have to first consider in our solution what direction is going to give us the maximum rate of change. Oh my goodness. The directional derivative is defined as a dot product. And we know how dot product's defined, right? If we have the, how many recall that the dot product of vectors A and B is equal to the magnitude of A, of the vector A, times the magnitude of the vector B, times the cosine of the angle between those two vectors. How many recall that? Okay, yeah, absolutely. So we're going to make use of that. We're going to make use of that. We can therefore make use of that definition, but the vector u is a unit vector. So the directional derivative of a function really is equal to the length or magnitude of the gradient vector times the cosine of the angle theta. And the angle theta is the angle between the unit vector and the gradient vector. But we note here that the directional derivative will be maximized in the direction of the gradient vector, because what's the largest value that the cosine of theta can be? 1. Right, and cosine of theta equals 1 when theta is 0 degrees. So that means that when your vector, your unit vector, is pointing in the direction of the gradient vector, that gives the maximum directional derivative. And so the gradient vector points in the direction of greatest increase. So in order to find the maximum rate of change, we look in the direction of the gradient vector. And so our surface increases fastest in the direction of the vector 1, 2, and the maximum rate of change is going to be the square root of 5. Please let me know if you have any questions. Okay, and I'd like to graphically show you what this result means as well. May I go to the next page? Does anybody need more time to copy? Okay, Malik, excellent. All right, Yunu, very good. Okay, Ellie, very good. Okay, well, all right, let's go ahead then. And Madeline's ready to roll. Okay, good. Okay, so on the next page here, what they've done, I actually took these from the textbook, figure 7 and figure 8. So figure 8 just shows a picture of this surface. Remember, our function is equal to x times e to the yth power. Okay, and that function clearly, if we're at the point 2, 0, okay, and we're looking in the direction of 1, 2, that's, you know, that's clearly going to increase, and they're showing it. But what they have up top is really the most important picture. Here's the point P. The point P has coordinates 2, 0. And they've drawn the level curves for this surface as you move out from the origin. Okay, they've drawn a contour plot. Now, the gradient vector, okay, the function increases fastest in the direction of the gradient vector. And you can see the gradient vector, perhaps I can highlight it here, because it'll be in the recording too. There's that gradient vector right there. And what do you notice about the gradient vector with respect to the level curves? The gradient vector, like this is a two-dimensional picture, so the gradient vector is crossing over the level curves. What's sort of interesting about the angles at which the gradient vector crosses over the level curves at? They're all parallel angles, that's right. And what kind of angles are they? What do they appear to be? If we were to, like, for instance, if we were to like this angle here, sorry, I got to do it. One moment. Come on now. So look at this. Sorry, let me try this again, class. Here's that gradient vector. And look at these angles. These angles all appear to be how many degrees? That's right, 90 degrees. That's right, Ellie. That's right, you knew. These angles, and maybe I'll now draw it. Let me get my pen out here. My thing. Don't all of these angles appear to be right angles, class? That's no accident. That is no accident. The gradient vector at a point will intersect the level curves of the surface at right angles. It will do that. Okay? That is a property of the gradient vector. Okay, are there any questions before? I want to look at one more example, and then I'm going to let you have a little time to work. I'm going to let you have a little time to work. Let me show you something here. Let me go to the ebook. One moment. Where is the ebook here? Hold on. Yeah. One moment. One moment, everybody. So this is actually a figure in the textbook, figure 13. And you'll have a MATLAB assignment that relates to this. It's not of the first 3 MATLAB assignments. It'll be one of the later ones. But what they've done here is you have a function. Okay, our function equals x squared minus y squared. Okay, and let me see. One moment here. Let me let's see. Can I just like, can I color that? Yeah, that's what I want to do. So what they do is they draw the level curves of this surface, and this surface is actually going to be a surface. We call it a saddle. It'll have what's called a saddle point. Okay, if you want to know what the surface looks like, actually, hold on. I'll show you. Well, it's x squared minus y squared, but it looks like a saddle of a horse. That's what the surface is going to look like. It's that's, hold on here. You know, you might have taken the words right out of my mouth. Got to be a little careful here. It's a hyperbolic paraboloid. That's what it's going to be. If you go in section 9.6 and look at table 2, at the bottom left, they show a hyperbolic paraboloid. Okay, and that's what the surface will look like. And they've drawn the level curves. Let me see. I think it's probably worth me bringing up. Let me find it here. Hold on. Let me find this in the book here. It's worth finding it. Hold on here. It's worth it. I just gotta, you know, get. Hold on here. What I'm doing is I'm locating the table. Hold on, everybody. I don't know if I can make it. I can't move it. I can't. Hold on, everybody. Just give me a moment here. What I'm doing is I'm looking at table 2 in the book, but can't seem to make the table appear. Like in the ebook, you know, they give a piece of the table in the book. They give like a part of it, and tell you what. Let me hold on. Somebody's yeah. One moment. I'm gonna find it. I'm gonna find another way to get it. One moment. Just give me a moment here. It's not working too well. Just be patient, class. I'll see if. All right. Well, I'm going to just let it go. I'm going to let it go. You can look. You just look in your ebook if you want. Look in your ebook now, section 9.6, table 2. But let me go back to the picture here. I mean, you can all see it there. You can all see it. Okay, so the surface basically looks like the saddle of a horse. Okay, and if you know, so like going along one direction, it looks like you're increasing as you move along the one axis, but if you move along the other axis, the surface is decreasing. So the surface increases in the direction of one axis, but then if you move in the direction of the other axis, the surface is, so in one direction the surface is increasing, the one axis, the other axis the surface is decreasing. And what they've done is they've drawn a contour map. And the gradient vectors, which are those blue vectors there, and MATLAB can do this. MATLAB can do this for you. I can actually, I'll see if I have a program that shows this or something like this. But the gradient vectors, the blue vectors, point in the direction of greatest increase. So you see there, if you look at the contour plot of the surface and look at the gradient vectors in Figure 13, if you move along the x-axis to the right, is the surface increasing or decreasing? So it's increasing. So I'm taught, like starting at the origin, moving in the direction of the positive x-axis. The gradient vectors are they're what's happening to the gradient vectors as you move along the x-axis. The gradient vectors are, well, they're going from 6 to 9, but the gradient vectors point in the direction of greatest increase. And those gradient vectors are perpendicular to the level curves. But also what's happening to the gradient vectors as you move out along in the direction of the positive x-axis. they're increasing in magnitude. So that's right, Ellie. When the when the vectors get longer, that means they are increasing in magnitude. Okay, now if you move out along the negative x-axis, okay, the gradient vectors are also getting larger. And is the surface increasing or decreasing as you look to the left from the origin? So look at the gradient vectors. Go along the negative x-axis. Okay, is the surface increasing or decreasing? That's right, it has to be increasing because those blue gradient vectors point in the direction of greatest increase. So the surface is increasing. Are there any questions on that? Actually, if we look on the right, we do see the values of level curves 3, 6, 9. The curve, so the surface is increasing. Now let's look along the y-axis. Okay, if we were to go from the positive y-axis towards the origin, and look at the gradient vectors, are the gradient vectors pointing up or down? So I'm looking at the positive y-axis moving in towards the origin. The vectors are pointing downward. Okay, so downward is the direction of greatest increase, right? So that means that if I were to go from the origin and go upward, okay, upward towards in the positive y direction, if I went from the origin and looked in the positive y direction, would the surface be increasing or decreasing? Then it's decreasing. That's right. That's right. Because you see, if the vectors going inward towards the origin, those gradient vectors, well, actually, but let's also think, what's happening to those gradient vectors as we move into the origin? If we're looking at the positive y-axis, and we're moving from positive y-axis towards the origin, the gradient vectors, are they getting larger or smaller? They're getting smaller. They're getting smaller. So what's that telling you about the surface? If the gradient vectors are getting, the surface is increasing, but it's plateauing. That's right, it's plateauing. It's leveling off. Okay, are there any questions on that? Please ask if you have a question. Please ask. So, three-dimensional surfaces are, even with MATLAB, when you graph a surface, to really see the whole surface over maybe a certain values of x, certain values of y, oftentimes you have to rotate the surface to see it, to see the behavior of the surface. But these two-dimensional plots, the level curves, the contour plot with gradient vectors superimposed over it, tell you a lot about the behavior of the surface. Okay, so that's why they have value. That's why they have tremendous value. Okay, I have one more thing I want to talk about from section 11.6. One more thing here. Let me find it. And then we'll be done with 11.6. Yeah, this here. One moment. Get that off there. Okay, tangent planes to level surfaces. Okay, so remember, level surface is if you if you take a function of x, y, and z, and you set it equal to a constant, you're going to get a surface. If you set it equal to a constant k, if you change the value of that constant, you're going to get different level surfaces. Okay. Well, if we take our function of x, y, and z and set it equal to a constant, then we will get a level surface. We will get a level surface. And, you know, we'd like to be able to find the tangent plane to the level surface. So here in figure 9, this is the scenario we're talking about. Here's a surface, and you have a tangent plane to the surface, and you have a curve on the surface and a point P on the curve, and from the point P you have the tangent vector r prime, okay, and you have a gradient vector. So if we can think of these, I want to say this the right way. If you think about this, see, I have to kind of go back and forth, but yeah. So if you think about the curve C, the curve C can be traced out by a vector function r of t. So the coordinates x, y, and z on the surface can be, if the vector function traces out points on the surface along that curve C, those coordinates are functions of t. And so we can think of the function of x, y, and z equal to k. We can think of those coordinates x, y, and z as functions of t. Well, by the chain rule, okay, if you were to differentiate the function with respect to t, then I want to say this the right way, then this would be your chain rule. This would be your chain rule right here. Okay, because what you have here, let me just show you. You have a function, okay, of x of t, y of t, and z of t. So the function is a function of x, y, and z, but x, y, and z are themselves functions of t. Okay, so if you have a function of x, y, and z equal to some constant, and you differentiate that function with respect to t, and you would do it both sides, right? What's going to happen is, by the chain rule, and by this, this flow chart, the left-hand side here, by the chain rule, is going to be the partial derivative of f with respect to x times the partial derivative of x. It's the derivative of x with respect to t, plus the partial derivative of f with respect to y times the derivative of y with respect to t, plus the partial derivative of f with respect to z times the derivative of z with respect to t. And that equals 0. Are there any questions on the chain rule here? All right, well, could we write this as a dot product? Could we write this on the left side as a dot product? What do these partial derivatives here, what do they comprise? What vector contains these first partial derivatives? You remember from section 11.6? Well, here's what I'm trying to say. Here's what I'm trying to say. I can write this sum on the left as the dot product of these two vectors, right? So what I'm asking is, what's this vector here? I'll give you a hint. It begins with a G. First letter G, second letter R. The gradient vector, that's right. So this here is the gradient vector of your function. And you're dotting it. Oh, what's this vector here? What's that vector? Well, it's a vector of derivatives. Tangent vector, good, R prime of t. So we get this result. We get that the gradient vector dotted with R prime of t equals 0. Okay, so I derived that result completely here for you. Let's go back to the ebook. It's all in the recording, of course. Let's go back to the ebook now, and let's go. Here's the picture that supports this. Okay, we have a level surface, and there's a point on the level surface. The gradient vector of the function at that point is perpendicular to the derivative of the tangent vector at that point P. Well, at that point P, there is, that curve C passes through the point P. So at some time, the curves, the R of t sub 0 will equal point P. And so R prime of t sub 0 is that derivative vector. Absolutely amazing, absolutely amazing. Okay, and so we end up with this result. We end up with this result here. Okay, but what we can do here, and I want to say this the right way. One moment here, one moment. Yeah, this is the point that we're trying to get at here. This equation 18 says, okay, it says that the gradient vector is perpendicular to the tangent vector R prime of t to any curve C on S that passes through the point P. Okay, so the equation, basically because of this, we found that this is the equation of the tangent plane. This is the equation of the tangent plane of the level surface at the point P. Or at the point P, yeah, at the point P. So do you see this? Based on the picture here, figure 9, does that make, I mean, there's figure 9. You can see the gradient vector. Okay, it's perpendicular to the you know, to that derivative vector. So essentially, like, I want to say this the right way. Essentially, I mean, what you're used to seeing, right, is A times, for equation of a plane, A times x minus x sub 0 plus B times y minus y sub 0 plus C times z minus c z sub 0 equals 0. And what they're doing is A, they're replacing that with the partial derivative of this function for the level surface, evaluated at x sub 0, y sub 0, c sub 0. And then B, they're replacing that with the partial derivative of f at x sub 0, y sub 0, z sub 0. And then C, they're replacing that with the partial derivative of big F function with respect to z at x sub 0, y sub 0, z sub 0. So the A, B, and C are replaced by these partial derivatives evaluated at the point x sub 0, y sub 0, z sub 0. And this allows you to get the equation of a tangent plane to a level surface. Absolutely amazing. Absolutely amazing. So let's see how this works then in practice. Let's look at an example here, and then you'll be ready to do some classwork here. And I thank you. I know normally we have a break by now, but you kind of had a break right at the beginning of the class, but I guess probably you like breaks in the middle more, right? So, okay, let's okay. Okay, so let's get to an example here. So example 8 says find the equations of a tangent plane and a normal line at the point -2, 1, -3 to the ellipsoid given below. Okay, so ellipsoid looks like a football, right? Again, you can go to table 2 in section 9.6 and see what an ellipsoid looks like. It looks like a football. And the picture below, I mean, we're at the point -2, 1, -3. I mean, there's a picture of our ellipse, and there's the tangent plane to this. I'm sorry, there's a picture of the ellipsoid with the tangent plane to the ellipsoid at the point -2, 1, -3. All right. So so we know a tangent plane exists. If we want to find the equation of the tangent plane, if we want to find it, okay, then based on the formula, okay, we have to compute the partial derivatives. Well, first we define our function f of x, y of z. We define it as x squared over 4 plus y squared plus z squared over 9, because that's being set equal to 3, right? That function of x, y, and z is being set equal to 3 to give you the level surface, to give you that ellipsoid. But now we want the equation of the tangent plane to that ellipsoid at that point -2, 1, -3. So what we do is we take these partial derivatives of the function, evaluate them at the point -2, 1, -3, okay, and then we can construct the equation of the tangent plane. Okay? So are there any questions on that? I mean, it's absolutely amazing what we can do, what you can do given the knowledge you've learned. How many are feeling okay with this? Or, I mean, I know you have to practice, but how many are at least feeling okay with section 11.6? Fiona is good, excellent. Charles is good, excellent. Malik and Ellie, wonderful, wonderful. And Juliana, okay, all right. I will stop the recording.